Hello students, today we're going to look at section 7-5, which is exponential functions. Now let's just review a minute. We've done linear functions, and linear functions were in the form of y equals mx plus b or y equals mx, and they had a constant rate of change, which was the slope, and that was y over x or rise over run, and they formed a line. Well, we're going to look at an exponential function and how it's different from a linear function to start off with. So an exponential function is written in the form of y equals ab to the x. Now we still have an x and a y, but in this case x is an exponent. That's important to notice because that affects everything. So in our exponential function y equals ab to the x, it's important to know that a cannot equal 0, because then we wouldn't have anything. Then we also need to know that b is going to be greater than 0. Okay? B will not be a negative number. It's going to be greater than 0. It can be a fraction, but it is going to be greater than 0. And the other thing we also need to know b is not going to equal 1. It's still going to be greater than 0, but it can't be 1. Because if it's 1, then that makes it a linear equation. And we don't want a linear equation, we're doing exponential. Okay? So as you look at exponential functions, something that you need to remember is it's y equals ab to the x power. And notice that the x is only on the b, not on the a. Okay, a would be what we would consider slope in linear, but it's not. That's not the case here. A does not equal 0. B is greater than 0, but b does not equal 1. So let's graph an exponential function and kind of see what it looks like. And we're going to graph the exponential function y equals 3 to the x power. And I know there's no a in there, but that's okay. We have y equals 3 to the x. So I'm going to set up a table, and just for showing purposes, I'm going to do 3 columns. And we're going to have our x here, and then we're going to have 3 to the x here, just so we can see what it looks like, and then we're going to have our y values there. And like we normally do when we graph anything, we're going to start with -2, -1, 0, 1, and 2. So if I'm going to start with -2, I'm going to say 3 raised to the -2 power, because x is -2. And I know from negative exponents that means I need to move it down to the denominator. So it's going to be 1 over 3 squared, which is 1/9. And so I have 3 to the -1 power, and that's just 1/3. So when x is -1, y is 1/3. 3 to the 0 power, now we love the 0 power because it just equals 1. So 0, 1. And then 3 to the first power is just 3, and 3 to the second power is 9. So now we're going to graph these on our coordinate plane. Now, if you don't have a coordinate plane in front of you, that's great. That's not a problem. Just draw your x-axis and y-axis, and we can estimate. But it's not a problem there. So we're going to start with -2, 1/9. So I'm going to go cross -2, and 1/9 is going to be really close down there. And then -1, 1/3. And then 0, 1. 1, 3, and 2, 9. 2, 3, 4, 5, 6, 7, 8, 9. Okay? And you notice there is nothing close to a line in this. It is what we call a smooth curve. So we're going to take our dots and we're going to connect them into what's called a smooth curve. And I'm going to try to do this as smoothly as possible. And then here, and then I go this way, and I put an arrow. And we have an arrow here. Because this is going to keep going up, and this is going to keep going here. But the deal is, this curve is never going to touch the y-axis. It's never going to touch the y-axis because it does not matter what number I choose, I'm never going to get a 0 for the x value. It's always going to be some fraction. It's going to be a tiny one, so this is never going to touch the y-axis. Because this curve is coming down here and it's approaching the y-axis but never touches it, that line is called the asymptote. A-S-Y-M-P-T-O-T-E. Okay? The asymptote is the line the curve approaches but never intersects. Again, it's called an asymptote. In this case, the asymptote of this exponential function is y equals 0. Okay? That is the equation of this line right here that the curve approaches but never touches. Asymptote. Now we also need to look at the domain and range of this. The domain for almost every exponential function is always going to be all real numbers, or actually any number, but we're going to write it differently. It's going to be written as negative infinity is less than the x, which is less than the positive infinity. That's another way to represent all numbers. I can go from infinity to infinity with my x values, and that will be on the curve. Now, but what about my range? My range starts at 0. It doesn't include 0. It starts at 0 and goes up to infinity. So the way I would write that is 0 is less than y, which is less than infinity. Notice there's not an equal to part here because it never touches the 0 line. It's always greater than 0. Anything greater than 0 is my range. Those are the important parts that you're going to need to be able to identify of an exponential function. The y-intercept, the asymptote, the domain, and the range. And you must write the domain in this form and the range in that form. So now we want to look at a table and a table of values, and let's see if we can figure out how we can tell if it's an exponential function as opposed to linear. So I'm going to take the same information that we had from the table in the first problem that we did, and I'm going to do it sideways, x and y. And we know our x was -2, -1, 0, 1, and 2. And our y values were 1/9, 1/3, 1, 3, and 9. So we've got that in our table. Draw a few lines. Now let's look at the change in the x's. We just added 1, added 1, added 1, added 1. Okay, that's important. Our x's have to be constant. Okay, and adding 1, or it could be adding 2, or adding 3, or subtracting 4, or whatever. But let's look at our y values. What's happening to our y values? And I'm going to look over here, and I'm going to start with 1, 3, and 9 because those are easy to deal with. How did I get from 1 to 3? Now, you might want to say plus 2, but that would make it linear, and this is not linear. Another way I got from 1 to 3 is that I multiplied by 3. How did I get from 3 to 9? I multiplied by 3. Well, how did I get from 1/3 to 1? I multiplied by 3. And how did I get from 1/9 to 1/3? I multiplied by 3. Because 3 times 1/9 is 3/9, and 3/9 simplifies to 1/3. So what I'm looking for an exponential function is a common factor. And as long as I have a common factor, not a common sum or difference, a common factor, and I have a constant up here in the x values, then I know I have an exponential function. Another example we can look at that is exponential growth, or we can test to see, is let's say I start with my x values 0, 5, 10, 15, 20, and then my y values I have 64, 32, 16, 8, and 4. Now let's see if this could possibly be exponential growth in here. So I look at my x values and I'm adding 5 all the way through. So that's constant. We're good. Now what do I do? What am I doing down here? How did I get from 64 to 32? Divided by 2, yes, but we're not going to put divided by 2 because that's not a factor. A factor is anything that we multiply by. And I know that dividing by 2 is the same as multiplying by 1/2. So 64 times 1/2 is 32. And 32 times 1/2 is 16. And 16 times 1/2 is 8. And 8 times 1/2 is 4. So I know that, yes, this is an exponential function because I have a common factor in my y values. So here are your practice problems for this video. The first practice problem says create a table of values for y equals 6 to the x plus 2 and then graph the function. What I would strongly suggest is that you use -2, -1, 0, 1, and 2 for your x values, and then create the table to show me what your y values are, and then graph it. Okay? And then for the second practice problem is determine if this table represents an exponential function. Check it out. Tell me if it's an exponential function, yes or no, but explain to me why or how you got that answer. Take a picture of your practice problems and submit them through Edmodo.